with the fourth example, part D, whether we can read a real world situation and be able to mathematically model what's happening. So in D, we're talking about an internet cafe. Don't know if they exist anymore. Internet cafes used to be like if you traveled around overseas in different spots, you can go to a place that had a bunch of computers, internet, where you can connect to other people if you didn't have your own Wi-Fi. All right, an internet cafe charged a fixed amount, so I'm really focused on that, per minute to use the internet. So that idea of fixed amount means it's a constant rate going forward. And if I'm going to think of what this could be, it would then have to be fixed, would have to be something that's linear. X is the number of minutes spent on the internet, and Y is the cost of using the internet in dollars. So let's look at the graphs that we have left and think which one could match that one with the internet cafe charging so much per minute. All right, so what things do I know I'm looking for? First of all, that I'm looking for something that is increasing over time. So the more you are on the internet, the more it's going to cost you. So it's going to increase over time. So obviously it's not going to decrease nor be curved. And so we do have some empty ones to look at. And we already used one empty one for one of the questions already. It's not curved. It's not a parabola where it's increasing then decreasing. Here this is increasing, but it's curved, so it's not a fixed rate. Where's the other one here? When I look at these, I haven't used this one yet. And so notice it's linear, it's increasing, and it starts at 0. Does that make sense? Because all the rest are curved on this page and there's no more graphs. So it's either this one or the blank one. So will this fit the internet cafe to model the cost of what it would be there? So this represents the number of minutes. And then the other axis is Y. So no minutes would be no cost. There's no start at the beginning. And then every minute it costs you so much money in terms of what's happening. And it's increasing at a constant rate over time. So G7 is what's going to match what we're doing. Now, a good question might also ask whether this internet cafe charges per minute in a way, or do they prorate with seconds and so on, so that it would be a continuous function. My thought, of course, would be it's probably not continuous, that every minute it costs you so much, and if you're between minutes, it would likely round up. So this would probably look more like a step, but here we go. So the equation, or the graph we just looked at, was linear going up. So which equation, would match with that graph then? So if I go to this sheet to understand which one, now we've already used A1, we've already used A3, we've already used A4. So we've used all of those. Which one have I not used yet that could be that linear function going up? And so these at the bottom half are not linear at all. So the only one we haven't used is here. Notice the y-intercept again is 0. So that means at the beginning it would cost 0, 0. 0 minutes means 0 costs. And then this gives me the rate that it increased by. So the equation we're looking at is y equals 3/4 x. So that's what I'm going to graph, only in the first quadrant. So I'm going to go 1, 2, 3, 4. So if I try to get a sense of how much this would be, if I'm only going to graph to 4 minutes, if I plug 4 into here, the 4's divide out, and that would be $3. And so I'm going to go $1, $2, $3 up here for the total cost. So at $1, how much does it cost? Or sorry, 1 minute. So this is number of minutes, and this is cost. So at 1 minute, how much would it cost? Plug it in, 3/4. Now, for my understanding, there'd be a hole here, but all the way up to 1 minute would be $1, or would be 34 cents. Then when it goes up to after 1 minute, you plug in 2. Now 2 goes into 4 evenly. So here, even if I do this on the side, so if I plug in 1, the answer is 3/4. If I plug in 2, you get 3/4 times 2. Even some common sense, 3/4 and double it. So that's 6/4. How much would that be? So you can see that's $1.50, right? And we want it in terms of money. So the next mark from 1 minute to 2 minutes would be $1.50. So find where you think $1.50 is. It's going to start with a hole, and then at 2. The next one, if I plug in 3/3, what's 3 3/3? So 3/4, so that's 9/4 is how much money. So if you think of it as 9/4, it's $2.25. See if I can line this up a little bit better. If I look over it without graph paper. And then 4, I just mentioned that if you plug in 4, the 4s divide out and you're left with $3. So from 3 up to 4, and then that pattern would go over and over and over again. If you if you connected the solid points here, if I had done it a little more accurately, that line would be y equals 3/4 x. But in our real world situation, it's not continuous in our understanding of how it would be charged. So if you used 1 minute and 30 seconds, they're just going to charge you 2 minutes. So every minute you get charged that. So if you're in between minutes, they're just going to round up to what that nearest minute. That is real life. It's going to be more like a step when you look at it to each one. But if you connect the ends of the step, that would make the line 3/4 x. All right, next real world situation. Real world. Used to be a famous show on MTV when people watched MTV. E. Let me read the situation. So we're done with this. Here we go. E. So the next situation has to do with that kettle. And so it says a kettle of boiling water cools in a warm kitchen, and then the time that has elapsed in minutes and the temperature of the kettle in degrees in Celsius. So what kind of things would be looking for off the graph when I look for it off the graph? Let me just organize myself here for a second. So we have our graphs, not the ones we've already used, so we can cross them out, one graph per situation. And then what are we looking for? And then we can go from there. So here, if something's cooling over time, it starts with a hot temperature, and then cooling over time, it is going to decrease. But what's the challenge with this one? Is that the kettle actually starts with the temperature on the y-axis. So the initial time at 0, what's the initial temperature of the kettle? There should actually be a value here on the axis and not an asymptote. So y could have been the answer. Instead, it has an asymptote that prevents it from being that. We have an empty one still, so it could be that one. In G5, you can see that it's starting at a low temperature. It raises up and then goes down again. So that's not what we're looking at for ours, where a kettle of boiling water cools in a warm kitchen. So if it was cold, it warmed up and then went cold again, that could be it. But it started being hot and then cooled down. So this one is not going to be it. Here, this is increasing, so it cannot match our real-world situation. This one decreases and then increases, cannot be the one where the temperature goes down and then rises again in a cool room, no. Here, I want you to notice it is decreasing, and notice on the axes we actually have a value. So we have a value there, and then the temperature decreases over time. Here, it goes up and then down in temperature, up and then down in temperature. It does not match, and this one increases. So it's either going to be the blank one, or does this really match what we're looking for? And the answer is, this one matches in terms of what's going to happen to that kettle as it cools with temperature. Now, when I see this equation, which one do you think will match that equation? So what does it look like that it could be? So there's no vertical asymptote, but there definitely looks like a horizontal asymptote. So let's look at the equations of what could be decreasing with a curve like that, but with no vertical asymptote. So let's look at the equations again. We'll cross out the ones we've already used. So we've already used these 4. So this is where we're at right now in terms of which one it could be. So here we have an asymptote at 0. So there's no value. We need an initial temperature at 0. So it's not that one. Cube root, even though it doesn't feel like it, actually increases. Same thing with a square root. It increases over time. A parabola, increases and then decreases. Or decreases and then increases. Here again we have a parabola, so it's both increasing and decreasing. We have a sine function, which is a wave. It goes up, down, up, down. Then our last two are exponential. So if I plug in 0 here, both of these, this one is actually increasing, so I know it's not it. But if I plug in 0, it should be a reasonable temperature for what the kettle could start with, and so on. So let's say, and I'm pretty sure this is in Celsius, which means at 100 degrees it's going to be boiling. Anyway, this one's increasing. But why is this one the match for the equation? 0.27 is less than 1. When the base is smaller than 1 to the exponent x, this is going to be decreasing over time. Now, when I plug in 0 for x, anything to the exponent 0 is 1. So 20 plus 80 is what I'm left with. So it starts with a temperature of 100, which is the temperature that water boils at. All of that seems to put together that that's the equation we're looking at. So let me write this down. So a cooling kettle, what it's called. Can't even spell kettle. Cooling kettle. And through process of elimination and understanding increasing and decreasing, how it's increasing or decreasing, this is the equation. That we're looking at. So we're going to graph this, and then we'll answer the question and everything. I forgot to answer the question for the Internet Cafe. I just realized that. So the question of the Internet Cafe was, I'm just going to go back here. Okay, let me finish this one first, and then I'll go back to Internet Cafe. All right, so the cooling kettle, can I graph this? It kind of looks gnarly a bit, but we'll figure this out. So I said, first of all, when you plug in 0, the temperature is 100. So I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So it starts up here. There's the boiling water, and this is temperature. And the other axis is going to be time. And it's time in got all these papers going on. I'm sure you do. It's time in minutes. So minutes elapsed is going to be along here. So we have 1 minute, 2 minutes, 3 minutes, and so on. We might actually get values with our calculator because it's kind of not so fun to be able to calculate without a calculator. And that's okay. And we'll do that. You can go to Desmos, or if you have your own calculator still with you, you can do that. Okay, so plugging in 0, though, is simple. It's 100. So what happens when I plug in 1? And so I do have a calculator, so I'm going to plug in 1 with this. This is actually the calculator you'll use in calculus. So we have 20, and you can do it with any calculator, plus 80 times 0.27 to the exponent 1. So 1 will give you the answer. It already went down to 41.6 degrees. So I'm just going to estimate where that is. So 41.6. So 10, 30, 40, right there, right? Now this is going to be a continuous function. So as it's losing temperature, or it's getting cooler, every second it's losing it. So it's continuous all the way through. No steps, no breaks. It's continuously losing or cooling in temperature as it goes down. All right, I'm going to do the same thing. I'm going to plug in 2. So if I go back, I'm just going to change the 1 to a 2. When I do that and I plug in, I get 25.8 about. So right there, I'm just going to estimate what it looks like, and then I'll make a curve at the end. I'm going to use 3. I'm just doing a quick table of values. And you get 21 point. Notice that it's flattening out a bit. So right at the beginning, it drastically cools, and then it starts to flatten out. So 21.5, I'm going to estimate where that is, or 21.6. And then I just said I'm going to do one more. So at 4, and then I'll just follow the curve going down. I get 20.4, so it's definitely flattening out right around 20. Now, in this model, the coolest the water can get when you look at it is actually 20. So eventually this number will get so small that when you add it to 20, it'll just be 20. But it can never be less than 20 because this answer will never be negative. So wherever you see 20, that's going to be an actual asymptote. So this is an exponential. It has a horizontal asymptote. And at what number is the horizontal asymptote? And it's 20. That tells me that's the temperature it's going to get closer and closer and closer to. You can think of that as the room temperature of a room. So 20 degrees Celsius would be, whatever it would be, around 70, 68 degrees Fahrenheit. That's a reasonable room temperature. So if you take a hot kettle that's 100 degrees, over time it's going to get closer and closer to what the temperature in the room is. So this is continuous. It doesn't stop there. It keeps going on forever and ever. But notice how it's going to flatten out at 20 degrees. Now I'm going to answer the question. So the question was, where is it? Where's my kettle? There it is. So the question is, what is the temperature of the room? Hey, we talked about that. So the temperature of the room is, what did we say? And the answer is 20 degrees Celsius. So what we're adding at the end, it will never get smaller than that number. It's going to get closer and closer to the room temperature. This exponential will never have a negative answer. And actually will never be 0. So it'll never be 20, but it'll be closer and closer and closer and closer to 20. So the temperature of the room is 20 degrees Celsius. I'm going to go back to the internet cafe question, right? I didn't answer it. So the internet cafe question, when I go back, what was the internet cafe question that I did not answer? So the question is how much $8 would buy, I think. What did I do with it? I know it's somewhere here as I go flip-flop with these pages that I have. Oh, I know, it's on the back here. Oh, yeah. So the question was for the internet cafe, how many minutes will $8 buy? So understand this, that you're given 8 minutes. Minutes is the x-axis. So what I would do is, where there is, it says how much will what did I say? $8 or 8 minutes? How many minutes will $8 buy? I think that's what I said. Yeah, how many minutes will $8 buy? So that means what you're given is actually the cost. So $8 is how much it costs, and 8 represents the y. So we're going to write that equation down, and we're going to solve for x to know that how much does $8 buy? How many minutes would you get on the internet for that? So to get x by itself, I would do the reciprocal and then simplify it. So the reciprocal get x by itself. 4 times 8 is 32. Remember, we're going to have to round down for this. So 32 divided by 3. So if I go to the nearest whole number, I don't want to go to 11 because 11 won't be able to solve that for me. So 32 divided by 3. So $8, when you do the reciprocal, will get you about 10 minutes. So 32 divided by 3 is 10 point something. It's not quite 11. And so you have to round down in terms of it. So up to 10 minutes, that will cost you the $8. That's how much you would get for $8. So you couldn't go up to 11 minutes because you need $9 to get to 11 minutes. All right. Sure, I'm just double checking I did the math okay. So the reciprocal, 32 divided by 3. That is almost 11, but not quite. So 10 minutes is what it would get you. All right, back here, E, we answered it. We have one more, and then we're done our assignment. So F, let's look at F. F is a Ferris wheel. And a Ferris wheel turns around and around, of course, over and over again. And X is the time, and then Y is the height of a seat from the ground in meters. So whatever seat you pick, or whatever direction you go, so let's say it goes in this direction, it's going to get higher and higher and higher, and then it's going to get lower. And then it's going to get higher, and then it's going to get lower. So it's going to increase, then decrease, increase, then decrease. Is there a graph that goes up and then down that can describe the height of that seat over time? So I remember this one, so I'm going to go directly to it. Can you see this in terms of wherever the seat starts at, right? That it's going to go up, and then it's going to go down, it's going to go up, and then it's going to go down, and so on. So this is going to follow a sine function in terms of what it's going to look like. Or it could be cosine, but there is no cosine. There's only one trig function in there anyways. So let's write this down. This is the Ferris wheel question. And what's going to match it is the equation that's a trig wave. So if I go to the equation sheet, which one is the trig equation on that sheet? So make sure I cross out the ones I've already used. So there's 4 I've already used. I used this one here at the bottom. And the trig that we're going to use right now is right here, A10, this sine wave. So we have y equals 30 plus 30 sine 18x. And we want to graph that. But just in the first quadrant. So it's over time. Now the x-axis is going to represent seconds. So this one's time. The y-axis is going to represent the height of whatever seat that is. So let's see what's going to happen here. What I want to know is where it starts to begin with. So if I plug in 0, and you can use your calculator if you wanted to, the value of that at 0, sine at 0 is 0. So all of this would be 0, and you'd actually start at a height of 30 when we start it. Then, as you graph it, it's going to go up or down from there, and we can plug in different times to see what would happen. And then eventually it's going to come back down, and then back up, and then up, down, and then back up, and so on. So I'm going to use my calculator. I'm not sure if it's in radians or degrees yet, so I'm going to try one and then the other. So right now, this calculator I have, I believe, is in radians. Yeah, it's in radians. So let's see if it's in radians to begin with. So I already told, even in radians, the answer would be that. So 30 plus 30 sine 18x. So if I go 18 times 1, what value does it make sense? So if it's in radians, it's going to go down in value. And I have a feeling, in fact, I'm even going to graph it right now. So if I graph that, I'm going to get rid of this. So if I type in 30 plus 30 sine 18x, and I graph it, let's change the window settings on this so it's a little bit nicer. So I went 0 to 5. I have a feeling that this is going to be above and below. Well, you can see it here in terms of what's happening. Now that's just 0 to 5 seconds. Is it really going to go up and down to 5 seconds that many times? I think they'd be thrown off the Ferris wheel. So let me change it to degrees to see if that's going to make a difference. So I'm going to go and change my settings. And then change it to degrees and see if that makes a difference with the graph. You could do this on Desmos too. So I changed it to radians. No, I changed it to degrees, I thought. Let me try again. So document settings. I changed it to degrees. If I tap it up here. So it still says radians. So let me try it a different way. Go settings there. All right, well, let's try this one. Degree. So now when I look at it, notice after 5 seconds it still is rising, it hasn't fallen yet. So I'm going to change the menu, the window, and I'm going to go and change it so it's not 5 seconds. So let's say it's 120 seconds or 300 seconds even. So like let's say how many minutes? So if it was even 3 minutes, that's what? 3 times, that's 180. If it's 6 minutes, 360. Let's just see what that will give us, if it makes sense in degrees. So it's going up and then down and then up and then down. That's 360 seconds. Let me change that window again. And I realize it's not going below the axis, so I'm just going to change that to 0. Oh, you get a sense of what's happening here and how long it might take to complete one cycle, if it's in degrees or seconds in terms of like graphing it. Let's use a little mathematical analysis to be able to figure out what's happening, to be able to graph it. So a sine wave usually starts in the middle. And because of this, our middle is actually at 30. It will then go to a maximum. This is our amplitude. We would add 30 to that and it would go up to 60, or subtract 30 and it would go down to 0. So we know it goes up to 60, in the middle is 30, and then the minimum is 0. So if I time this out, 1, 2, 3, 4, I can see that 30 is in the middle, 60 is at the top. So this is going to start in the middle. Because it's positive, it's going to go to the top and then back to the middle and then the bottom and then back to the middle, and then you can see this wave that's going to happen. Now, part of this real-world situation, I think, is inaccurate, obviously. So is it going to take 3 seconds? I mean, it's going to take 1 second to get to the top and then 2 more seconds to get to the bottom. I don't think physics would allow that Ferris wheel to be that fast and not like kick you off if it's going at that kind of a speed. There's some centrifugal force going on there. But the process, in terms of being able to analyze it, that's good. That we know it's a sine wave and it goes up and then down, and that we have the ability to graph this. That we understand what's happening in terms of that. Well, here, we could also find the period. So if it's in degrees, the normal period would be 360. So divide that by 18. How long would it take to complete? So actually, this is probably a little bit inaccurate. So if I went 360 divided by 18, one cycle would take 20 seconds to get around. Is that accurate or not? I'm not sure. If you take that and divide it by 4, then every 5 seconds, so this should really be 5 and then 10 and then 15 and then 20 would put you back into the middle. So every 20 seconds, you get back to where you were. Is that accurate in terms of it? I'm not sure. 20 seconds, is that the length it usually takes to complete one cycle? Maybe, if they're not stopping and putting people on the Ferris wheel. So the period we found to be 20 seconds. If I divide by 4, I can understand that every 4 sections of that, it's either going to be the middle, the top, the middle, the bottom, and so on. So following the pattern, every 5 seconds, so 20 seconds, in the middle will be the middle, then the top and bottom, you can partition this wave and be able to graph it. Oh, there's one question. How long does it take the Ferris wheel to turn once? And we just answered it. This answer here, it will take 20 seconds to turn once. So how long will it take to complete? And the answer is 20 seconds. And we found that, and we had to have a better understanding. Is it going to be in radians or degrees? What made more sense in terms of completing one cycle? So radians had too short of a situation where it did not make sense in terms of a real world situation, but degrees made more sense. All right, you did it. Mr. G Math, over and out. Good job doing your work. Till next time.